to now we'll have to use some codes and write some simple codes yourself. We use the ALPS project for that. They call it cooperation to write some open the source software for physics. There are the people involved from ETH, some here, Bela, Trigid, Jan, Tamar. Get up, please. Those people can be asked if you have questions. Then there are the people from Munich, from Stuttgart, Dresden, Göttingen, Wyoming, Harvard, UCSB, Columbia, Tokyo, Toulouse, and from Poland. Yeah. So what is the name ALPS? ALPS stands for Algorithms and Libraries for Physics Simulations, and it's only by chance that it was invented high up in a mountain village in the Swiss Alps. So far, most of the ALPS workshops have been in mountain regions. So Boulder also fits with that. You need to have a mountain nearby to talk about ALPS. The codes can be downloaded from ALPS.compass.org, though it seems we need to replace one of the Mac packages, which will happen in the next few minutes, and then it should work again. What was the motivation for starting the ALPS project years ago? The status quo was that every student wrote their own code. One specific for the one problem they had to study, but the methods became more and more complex. In the 70s, you could write your code in a couple of days. Nowadays, to write the full MRG code from scratch might take you, if you're good, about half a year. If you're not so good, it might take you 2 or 3 years. So it comes to a stage where if you want to use really the latest methods, unless you really focus on and numerical, it became impractical to use the latest methods. So with ALPS, we want to share the codes, we want to make them flexible and generic so that they work for more than one model. We want to have some libraries that simplify the code development and some common file formats to simplify the exchange and the creation of data. ALPS is built on C++ and Python, as well as some standard formats as like the XML and the HD5, and for parallelization mostly MPI. In ALPS there are a few levels. The lowest, you could say, are the standard the data formats, the same. We have the file formats for the inputs and outputs of the codes. The next level are the libraries that can read those files, write them, write data, run programs, the parallel, make plots and so on. Then what we mostly use are the evaluation tools for data and the analysis, the jackknife, the binning analysis for plotting data, and also to record provenance information. Who outside of my group knows what provenance information is? You will all, I think, Thomas, you know that, but the others will learn about it. And then we have the applications, and that was actually the main starting point of ALPS, that experimentalists asked us, we would like to use your codes to get some data 4 models and you want to then pick some data. And so that was the starting point, but I think the tools are the more important even. What do we have in ALPS? We have simulation codes for the Monte Carlo, for exact generalization, for FT and the DMG, and you will learn to use most of those codes in the coming weeks. And the motivation for those codes were those are some established the methods that they are mature, and there's an increasing demand from people who want to use those codes for some quick calculations of some quantum magnet, some 1D spin chain or whatever. Now I want to tell you a bit about the parts of ALPS, the technical details. And the first is, why did we use XML for the input file formats? For this XML, XML stands for Extensible Markup Language, and it essentially looks somehow like the HTML. There is no chance, but that is because actually HTML is one format in XML. So we have some tags that mark what this content here is about. Then we have some, so there's a tag here which here opens a block. Here's the ending block with the slash in front. If you have a tag that is just one tag itself and closes immediately, like here, then you place a slash at the end. Then we have some contents, like here a paragraph in this p tag, and we can have some the attributes, like here we have the image tag as the source, the attribute, the value, the image.jpg. Now, why do we want to use XML? Look at this example. Here's my simple old plain text input file. The parameters are 10.5, 10,000, and 1,000, and then the results might be in the output minus 10.451 and 0.043. Now here I might remember for a couple of months, the first input parameter is the system size and the next is the temperature. I might add some the more common state, but it is very easy to forget what these were. If we do that in XML, like here, then I can write the tag like the parameter name equal L, and then the value is 10. And T is 0.5 and so on. So here I know what these were. Now let's imagine I change my format at a later time, and now realize that the random number generator I've always used was bad. So now I want to add another the input, namely the type of random number the generator used, and I add one more line here that the random number generator is a Mersenne twister. Now any code that relied on there being a number, and then the output, that code breaks, because now I have 5 numbers, or the input 5 numbers and then a string. So if I rely on the position of the argument, then I break my code that way. In XML, I use just some new tag, a new the parameter, and some new random the generator tag. The old codes can be written in such a way that they simply ignore any new tag they don't know about. so that this file can still be read by the old code. And the new code can still read the old files. So it's extensible, and it's compatible with new file formats. So why do we want to use XML? It reduces the data out. I might remember longer what this L was about and what was the first number about. It increases the predictability of the data. It is extensible. It's a standard, and there's the style sheet language that I can use to convert it to text or display in the web browser. When you work with ALPS, you will never have to look at an XML file unless you want to. You can just view it in a web browser, and you'll see nice tables show up. The next format we use is the hierarchical data format, the version 5, HDF5. That's the binary format, hierarchical, the extensible, similar to XML, but the binary, and there are many the tools for that as well. Now let me show you how that can be used to run simulations with ALPS. For a typical quantum system, we'll have three inputs. The first is the lattice definition. Then I define the model, and then some parameters which link them. Like I say, the lattice is a square lattice, and the length is 100. The model is a spin model, and the spin model will have some couplings, JXY, JC, and the field H. Then I have some set of simulations, each inside a pair of curly braces for the temperature point 1, 2, 5, and 1.0. That defines my quantum system. Then on the same input file, I run one of three or four codes, Monte Carlo, ED, DMR, RG, whatever, and they all write the output in the same standard format. With the same inputs and the same output formats, which makes it easier to learn new code. Then you get the results, you read them, you plot them, you print things. So let me look at now the lattice and the model in a bit more detail. How do we define a lattice in ALPS? A lattice in ALPS can either be a graph. I can say, okay, I want to run a simulation on a graph that looks like this. I might have, this is my lattice, I might have a coupling on this, which is J1, and here J2, and here J3. But if you then want to have a square lattice, that's your size 100 times 100, and you don't want to enter a graph with 10,000 sides. So we can define the lattice as well, and we define the list of the lattices in the library file that comes with ALPS, but you can write your own ones as well. We have a lattice graph here, which is the square lattice, and that has a lattice of dimension 2 with the extent L in each direction. Inside the lattice, in a unit cell, we place kind of a unit cell graph fragment. That is, we place a single side, a vertex, and two bonds, two edges. So say in the unit cell here, I have one vertex, and have an edge of type 1 that goes from vertex 1 here to the target is the vertex 1 in the cell offset by the vector 0, 1. So there's one edge going from here to here. There's a second edge of type 2 that goes from here to here. And now the rest is replicated, and that gives me the square lattice. The unit cell has one vertex and two edges. I have two types. That means now on this edge and on that I can have a separate coupling strength. Next, we define a model. And for the model, I want to, for example, implement this model here. I think when we look at this, then it should be quite clear to us what the model is. That's a simple quantum spin model, and we don't have to discuss more. Because when you think a bit more, then you ask the question, okay, is that for spin 1/2, so spin 1 or spin 3/2? What is S plus and S minus? We have to teach that to ALPS. So again, there's then the model file, which includes, for example, a basis here. And the basis, this may say, okay, there's the basis for the sites. And on the sites, they are defined by a quantum number S set that goes from -S to +S. Then I have an operator, S plus, with this matrix element. And it changes S set by +1. An operator S minus with that matrix element that changes S set to -1. An operator S set that just has the value S set. It doesn't change anything. And now I build up my model from this, like my spin model. You say the basis is the spin basis, and on the sides I have a term that is -h times S set. And on the bonds between I and j, I have a term that is jxy over 2 times, and then just this model written down. I can now define a different term for each type of bond in the lattice, a different coupling strength for each bond in the lattice and so on, and that way make essentially any model I want. If you want to read more about that, we have the long documentation on the web page. For the models we'll use in the hands-on sessions, the models will all be already defined, and we'll use mostly the spin model that's the predefined already. The codes I already mentioned a bit.
Question?
Yes?
How do you specify that's the nearest neighbor?
How do I specify that? I don't specify it at all. I specify here I have a bond term, and I can specify that the bond term on those bonds of type 1, type 2, type 3, type 4. And then it goes through the lattice, and in the lattice I have the bonds, my edges. And they have certain types. Then it matches the type of edge to the type of bond term. So here I just say, if you find somewhere an edge of type 5, then use this term.
So you have to build a different lattice if you want like next nearest neighbor.
If you want to have next nearest neighbor interaction, you have to build a different lattice that has one more edge in it. Yes, correct. So we want to separate the model building from the lattice structure. And the coupling is through these terms, through these types of the edges. And we have some the bonus exercises to make you look at your own model and change the lattice and add some more couplings to it. And if you have the question, then just ask us. Now, ALPS can be run in 3 different ways. You can choose whatever way you are most comfortable with. You can run ALPS from the command line. That is most useful for the supercomputers and clusters. It will let you run the relations, but for plotting and so on, you're quite limited. So we recommend to use either Python or VisTrails. Python is a scripting language, VisTrails is a graphical workflow system. And first show you how to run ALPS from the command line. The advantage is it is easy to use. You just need a slow link to your machine. The disadvantage is the validation tools are limited. But I'll show you now how that works. Let me go to open a window here. We go here to one of the tutorials, and we have a file here, an input file palm2a. We want to run on the lattice is a chain lattice, the length is 60, the coupling strength J is -1. I want to do cluster updates on the classical Heisenberg model. I want to thermalize for the 15,000 sweeps, and then I want to update 150,000 cluster updates at temperatures 0.05, 0.1, and so on to 0.7, and then at higher temperatures I want to use a few more sweeps. So take this file. The first thing I do is I convert it to an XML file for ALPS. Now I have a large number of files. And this I have those in files. The input files from which I start, palm2a.in and the task 1 to 15. Those are these 15 typical temperatures. To look at those files, yes, we can just look at this palm2a.task1.in.xml file, and it's this ugly file with the parameters. It's hard to read, so I would prefer to look at this just in a web browser. palm2a.in.xml. And here's the list of the input files, and I can click on the input file, and I get the parameters in a table. Next, I run the simulations. Spinacity, the classic Monte Carlo one. I wanted to check whether it's here finished every 2 seconds. I wanted to write XML output as well. And I give the input file. Now it starts running. And the first simulation is finished, the second is finished. It will not take about half a minute. So, but we could stop it right now. Let me stop that here. And now I can look at the out.xml file. Want to look at it. And it shows me the first 5 ones are finished, the 6th one is unfinished, and the other ones are not finished yet. When I click on this first one here, then I now get as well when it was running, on which machine, and I get down there the measurements. And for some errors, it shows me actually that that's not converged, I didn't run it long enough. The error is not reliable, the binding analysis did not converge yet, so I should actually increase the number of sweeps. But here I have the results. So I have all I need, but I told you to make a plot now of chi versus t, just that takes you manually copying numbers over, writing scripts and so on. So I prefer to actually use Python or VisTrails instead, at least for the analysis part. Let me show you how that can be done. What is Python? Who here has used Python already in the past? That's about a third. Who has never heard of Python? That's very few. So Python is a scripting language, interpreted that is powerful. It has objects and classes and functions and all. It is easy to learn. There's a tutorial here that you can work through in one evening easily, or simply look at the examples, and you will learn from seeing the examples. And ALPS exports most of its functions to Python so that you can call that directly from Python. Creating the input files, running the codes, loading results, evaluating data, calculating the error bars, making plots, and so on. So let's see how that looks like in one of the examples. The first thing is we have to prepare the inputs. We make a loop here where I create a list of Python, the dictionaries that map a parameter to a value. So the lattice is a chain lattice, the temperature is this T, the value using this loop up here, the couple J is -1, and so on. Up there's a cluster updates, the model is Heisenberg in LA60. Once I've made this list, there's a function to write the input files, and I want them to have the prefix parm2a like before. And parms, that was this list of parameters. Then I run the application spinmc on this input file. That does exactly the same as we've done on the command line. After that, I can then load my data. Like I load the measurements from the files that start with the prefix parm2a, and in this case I wanted to load only the results for the susceptibility. Then I have that loaded. Now I want to make a plot of the susceptibility versus temperature. So I call a function here called xy, where the y value should be the susceptibility, the x value the temperature. Then I want to make a plot. That then shows us the plot immediately. And let me just start it for you. Let me start my Python interpreter. But before that, I want to open that file. I have tutorial. You have the files all there. That was this file here. And we can now copy and paste this into a Python interpreter. And first, let's just run the application. Now it's running again. And that takes a minute or so, so while that runs, let's go back to the slides. And the third version that we'll use is VisTrails. VisTrails is the workflow system that will be produced by the Bela soon. And essentially what we have here is a graph of the various functions that we call, and the lines is how the data flows down. You can load that, run it, just by clicking on the button here, like the execute, and you'll get the plot at the end. What are the advantages of using VisTrails versus the command line or Python? It has the GUI, it has the graphical, the workflow system. It's not that you write 5 scripts and run one script first and the second, third, and fourth script, but it's integrated in one workflow. You have the plotting integrated. You always have the complete history of anything you did available. When you change something, the old versions are still available. You can say, show me the workflow, how it was yesterday in the morning. Show me the workflow when Bela changed something. Show me the difference between last week's version that worked and today's version that doesn't work anymore. Or there was this great plot now and it didn't work yesterday. What was the difference? You can always go back to that. For any plot you create, you can always go back and find the workflow that produced it. Not that you look at the plot and ask yourself now, was that done with the latest version of the code or with an older one? Either use local updates or cluster updates. With the workflow system, that's always available. Then it caches all the intermediate results. When you change something and run it again, it only runs those parts that have to be rerun, and not all of it. The other advantage of having a workflow system is you can learn from the experts. Because when I do it in VisTrails, then I have my full workflow, from the input to the final plot, available in this one workflow. You can always see how did I do it. In a paper, you might just see I used that method and then I did a fit and got something out. Here, with the figures you produce, you can always retrieve the full calculation. And it records provenance information automatically. Before we come to the question, what is provenance, let's see what our Python script did. It finished the calculations. Next, we want to load these measurements. I could actually print this data here. When you print this, then you get a long list of things where the properties are. There's a long list in here. The susceptibility, the merization chain, and the result. For all the simulations. But I don't look at this now by hand. I call this function collect xy. Now I have the susceptibility collected in this here. And you see the y values and the x values nicely collected with errors. And next I just make a plot using the Python matplotlib plotting module, and I get my figure.
What software do you use for the plot? Software.
Matplotlib, that's the Python module. But what we can also do is we can just call ALPS.plot. Make new plot. Does it work? Ah, no, I have it's stuck in the figure. I have to close this. I mistyped. Was it PyAlps dot? Was it PyPlot? Here's it in GNU format, in XML format, or as a text file. It's easy. You can choose whatever plotting program you want. See, okay, now I prefer GNU, so you just dump it to GNU. Now let us look at the same thing in VisTrails. Space here. Here I have four versions: a classical Heisenberg chain, a classical Heisenberg ladder, a quantum chain, a quantum ladder. These are four workflows. Let me look at this classical Heisenberg chain workflow. Here's the full pipeline. Let me zoom in a bit. I think that's what to show them. We have the input parameters, we write the input files, we run the code, we get the results of the measurements and make a plot. I can just click on execute. Now it all runs. It runs so much faster than before because it actually realized that they had run that 3 days ago and the result files were still cached, and they found them, and because they didn't change the inputs, it found the old files. If they change the inputs, it runs it again. If it didn't change the input parameters, it finds the old files and just makes the plots directly. And here I have the plot. from the plot. I can then check out how it was calculated, and so on. But just click on execute and I get my plots.
If you do an incremental update of the binary, does it realize that as well?
If you do an increment up to the binary, I should then update the version number of the binary.
Right.
Then it runs it again because the version number changes the hash it computes. If you don't change the version number, then it assumes that it's still the same binary. So, before more of your VisTrails, what is computational provenance? It's something you all know. What does provenance mean? According to the Oxford English the dictionary, it is the fact of coming from some particular source of water. It's the origin of some data, or it's the history of the work of art, manuscript, and so on. So it's how did you come to get to some object at the end. So this question is, who created this result and when? What process modified some data? What process created the results? What was the input, the raw data? Parameters for the methods used? And it allows you to answer the question like, is the result okay, reliable or not? It's the full history of how you got to some data point. And that's something we rely on in science. It's not new. We had lab notebooks for many centuries. In order to reproduce the results and to have the evidence documented in case there's some problem later on. What is new is with the laptop or the supercomputer, we have large volumes of data. It becomes trivial for us to produce data. And we do many complex things. We select data, we fit it, change things, make plots, and so on. But do we ever document all of those things in a lab notebook? It's just impossible. It's so easy to produce lots of data that it has become impossible to document how exactly we did it. Who of you who has written a computational physics paper has ever documented every single step that went into the result? We can't even publish that in a paper. We can write, yes, we use this algorithm, but do we always write which random number generator we used, which random seeds we used? When we do a fit, do we write which data points exactly we discarded? No, because we can't actually do that, unless we automate it. And the problem I have, for example, is that I don't know exactly what I did 10 years ago. Or I don't know exactly how my student got to some plot. Now, what one can use to find it is to use a workflow system that automatically records all this information, like VisTrails. So that, for example, when you get a figure in a paper, you should be able to click on it and get the complete workflow that leads to that figure or number. That is how actually we should do science, right? But everything we publish, it should be possible to retrieve how exactly it was done. The workflow can be looked at. It could be included in the archive. It could be published with a paper. And then I might say, okay, I don't really believe you because I think you chose your fitting range wrongly, and if I change it a bit, then I get new results. So I want to be able to do that. That is in principle possible using VisTrails. They use that for the science papers. They started the project because in computer graphics, they had an algorithm published, input file published, and the output picture published, but nobody could reproduce it. It was essentially everything documented, but still from the description alone, you could not reproduce the output. So they realized they need the new system and started here at VisTrails, and we should be able to do the same in physics, and that's what we try with ALPS now. One example is if you have a figure from the tutorials or the paper, you should be able to just click on it, and you get the workflow loaded. You choose the version you want to have, you see the workflow, and you can rerun it. We have not done that yet in a paper, because ALPS 2 is too new, but we have done it for the tutorials. When you then look at the ALPS page, and go to the tutorials, let's go to the second Monte Carlo tutorial, which we will do on Friday. And down there we have figures. And this figure here is not just pasted into the web page, but figure here is retrieved right now when I load the web page from the server. The server runs the calculation, has it all cached, shows the figure. I can click on the figure, and it accesses the server, and now it has downloaded the VisTrails file here. I can open the VisTrails file in my VisTrails application. And yes, I trust this downloaded file. I should open. It runs the calculation on my laptop, and it should show me the figure. Let's see if this works. Yeah, here's the figure. And here's the other window. Here is the workflow that produced it. I can change things, change the axis parameters. I can change one of the axes here and set it to logarithmic. Want to have it on a log scale because things might look different on the log scale, and we can rerun it again. Plug in the log of the stability now, and it should show up. Here's now log of fibers and temperature. Now, just to finish, let me show a few the examples that the ALPS was used for. The first were the spin ladders, which are two coupled, the spin chains classically that would have here the nail order, the quantum mechanically, the two spins on the rung from singlet. It means that there's then a gap to the triplet on the rung, so there's a spin gap that leads to an exponential, the suppression of the stability here at low temperatures goes down here. In the experiment, there's an upturn again due to the impurities. We can model that as well, then fit it and get the coupling constants from the fit. And that's the fit, and it gives perfectly. Some experimentalists used the classical codes for some the molecular magnet, and did a fit with it. The Massachusetts used it to fit some organic quantum magnet to find the coupling strength as well. Used it for the cold gases in optical lattices, where we looked at the transition in a Hubbard model from the super bosons to the mod insulator. and looked at how the density profile in the trap changes when you change the equation u, and there will be many more things that you will look at in the hands-on sessions now. Before we come to that, I want you to install ALPS version 2.0 from the web page. Most of you should have received the installers. There was a problem with the VisTrails patch for the Mac. There's a new version on the web now.
Not yet.
Not yet?
In milliseconds of the.
Okay, then I'll check that. So the people who have a Mac can install ALPS, but not yet, and VisTrails, but not the ALPS VisTrails patch yet.
So anyone who has installed from the USB stick has to reinstall that?
Anybody who has installed from the USB stick has to just install something else on top of it. Something smaller.
VisTrails.
We have to. I'm not sure if we can manage that. Maybe if you can build it on upload, I can build it on my.
I built it just now on the Mac. So I will upload a new. So for those who have Windows or the Mac, there are 3 things to install when you go to the web page. So let me go to the web page. And when you go to the ALPS web page, the main page, and you go down to ALPS 2 download and installation. What you will have to install, it is written down here, is you first have to install VisTrails. Once you have installed VisTrails, you have to install the ALPS VisTrails extensions on top of VisTrails.
Can you explain it in detail for those people who have the stuff from the USB stick?
I'm about to do that. So you have it, so you install VisTrails and then the ALPS VisTrails extension. There's a new version of the ALPS VisTrails extension that you will upload in just a few minutes. It will then be here and you can just download it. It will be the ALPS VisTrails 2.0 v2, that will be replaced. There was a problem with the file we uploaded. And then, as a third thing, you have to install ALPS itself. So there are 3 installers in that folder. The ALPS VisTrails one will be replaced. Those who use Windows can just install the things that are on the USB stick. If you have any problems, just call out and ask for help. We have a few people here who have installed ALPS a few times, and that can help. Yes.
If I build ALPS from sources on Linux, and if I enable the support for VisTrails, do I need anything more, or that's it?
No, that's it. Yes.
Okay.
That's all that's needed. Yes.
So if we installed ALPS with the VisTrails, we have to remove the VisTrails and then download the new one that you're going to
You shouldn't have to remove the VisTrails. You will just get something that you install over it, and you'll be fine.
Okay. And you'll tell us when that's ready to download?
I'll tell you when it's ready to download, when we look at it. So you got, for macOS 10.6 for example, you got the VisTrails. The VisTrails you can just install. The ALPS 2.0 you can install. And this ALPS VisTrails extension, that will be replaced. So you just install the new version over what you have already, once you can download it. Don't forget to install all 3. And VisTrails should be installed first, also on Windows. Install first VisTrails, then ALPS VisTrails, and then ALPS. On Windows it's also first VisTrails, then ALPS VisTrails, and then ALPS. It is all explained here on the web page under installing the binary releases. When you read this, it should tell you what exactly you have to do with the files you got from the USB stick. The web page is alps.confus.org. Just enter that. And then go here, ALPS 2.0 download and installation.
Mac software requires you to have Intel processors.
The Mac software is compiled only for Intel processors.
So otherwise, I should run Linux.
If you, so you have,
I have a
our PC.
That's not the question here. If you feel that's the question that I was thinking before.
Yes, we had one person who responded that they have a PowerPC. I'm sorry, VisTrails is not compiled for that. One could do it, it's a major effort. So the best is if you look at somebody else's laptop and work with it.
Or if you have Linux, it shouldn't be that.
If your Linux kit does VisTrails work, so you use the Linux work. Yeah.
Yeah, no, I mean, like, on Linux and PowerPC should be fine, but OS X and PowerPC.
Yes.
I didn't get the information.
Then on.
It matters the order you download.
Download no, but,
I mean,
but
install.
you should install VisTrails before the VisTrails extensions, before ALPS VisTrails. So VisTrails before ALPS VisTrails. That's important.
If I install ALPS VisTrails first, should I uninstall everything and not reinstall?
If you install ALPS VisTrails first, then you simply go to Applications and move your VisTrails folder. So you have Windows,
Yeah.
then you uninstall. You go to the VisTrails directory and click on the uninstall folder. Or simply delete the whole folder. There's no further question right now, then let me pass on to Bela. I will make sure that you get this one file uploaded in a minute. Does it support that resolution? That's okay.
Okay, so I will now introduce the VisTrails interface and say a few more words on the ALPS modules and the internal data structures that we're working with and data types and this kind of stuff. Okay, so if you open your VisTrails, you will get something looking like this here. Two windows. This is the main window, so this is the VisTrails builder.
There's one button on it.
It sometimes works.
Sometimes not.
That works. It's not a,
Okay, I go with the mouse pointer. I can go with the mouse pointer. Yeah, okay, so this is the VisTrails builder, so this is the main window, and then this is the spreadsheet, which is already showed, which is used for showing the results. And in the VisTrails builder, the most important buttons up here are these, so pipeline, history, query, explorations. Those are the different views of a VisTrails file. Okay, so let me just, for example, look at this one. In the history, you have all the different versions that you have created. So whenever you change something in the pipeline, a new bubble will appear here, basically. Of course, it doesn't show all the bubbles. You have these plus and minus signs, so there's many intermediate versions usually. And then you can give names to versions by just tagging them. Those are basically the ones that you can find again afterwards. Now, if you select the version in this history and go to the pipeline, you get this tree basically. And the most important thing here are these boxes. These are the so-called modules. So let me show you in some detail what these modules are. So those are basically just Python classes It will implement some kind of transformation between the input ports and the output ports. So you have the little boxes up here, those are input ports, and down here you have the output ports. If you hold your mouse over them, it shows you the name. So this port is called palms, and it's of type parameters. So all these ports have a type and a name associated to them. What's the point of this type? The point of the type is that you can only connect matching ports. So for example, you have an output port of type Lattice, and I can drag it into the Lattice input port of this module, but I could not drag it into this, which is of type model. So I can't drag a Lattice to a model, and vice versa. All these types are actually really Python types or Python classes. And then for modules you have this menu here, so if you're looking for some documentation, you just click on the arrow, view the documentation. Not so much to say about the ladder lattice, but yeah, other modules will have more extensive documentation. And then there's this added configuration entry here, which will be important later when we work with source modules. Okay. Right. Okay, so I told you that you can set the input ports by connecting these to some other modules, because there's another way. So if you look at the right hand side here, you get a list of the input ports. You have L, Lattice, W, and Lattice library. And if I wanted to set something, you could just drag it down here, and for example enter 4, which would make a 4-leg ladder. If you actually look into the history now, you see that it's created a new version. So I started in this classical Heisenberg chain, and I've changed a few things. So I can just go back by clicking to this one, and you see that it's back to a 2-leg ladder. What do the colors here mean? It's just different users. So the yellow ones were done by user Troja. Okay, so the new binary installer, Mac VisTrails, ALPS Mac VisTrails is uploaded now. So you should be able to run it now. Yeah, so this is different colors here correspond to different users. Okay, so let me go back to the pipeline view now. If I execute it, again I should have the results cached on my computer. Or maybe not. Show this. Don't want to wait for it. But we get a few colors here anyway. So green means that it has been executed successfully. Blue means that it hasn't been executed for whatever reason, so it doesn't have to be an error. And then red, of course, means there's an error. Execution failed, that's just because I cancelled it because I didn't want to wait for it. There's more colors, I'll come to those later. Okay. Yeah, that's all I wanted to say now about the interface. So the query and exploration views up here. I'd say a few words about the exploration and the presentation, and the query is not so important at this point. So you can play around with this if you're interested, but it's not particularly important. So the most important views are the pipeline and the history view. And so I want to go through some of the presentation now, and then we're going to put together an extremely simple workflow, just plotting f of x equals x squared or something like this. Okay, so we discussed this, we discussed the views, the modules. Yeah, one thing I should say is how you enter types. So for example, this module takes a list of elements, which has the same syntax as a Python list. So these brackets and then strings on the right hand. Yeah, it's the same syntax that you would use also for dictionaries and so on. Okay, I wanted to say something about the different colors. As I said, green was executed. Yellow means that it was cached in memory, so that it was previously executed during that run of VisTrails, basically. Red means an error. Holding your mouse over it will give you the exception. And blue was not executed. Let me say a few words about the caching infrastructure. So the memory caching happens completely automatically. So whenever you execute a workflow, it will try to cache as much of the results as possible. Of course, if you quit VisTrails, restart it, all of that is going to be lost. So together with the VisTrails people, we developed another mechanism for caching on disk. So this is called the persistent cache. And that you have to enable as a user. It doesn't do that automatically because how should it know which files to store? And this basically remains forever, so it's not lost after you quit VisTrails. And it's achieved with the persistent file, persistent directory modules. So if you look at a typical ALPS workflow, so I think this is from one of the Monte Carlo tutorials. You have a few modules up here that set up the parameter file, so it goes down to here. Unfortunately, it's kind of hard to read. Can't change much about the colors. Then here you have the, in this case it's a one sparse diet module, so this module will actually execute the program. And so this will run for a long time. And then on the output module will give you a list of output files, and those we put into a persistent directory module. And this will tell VisTrails that I want those files to be stored on disk in some place where it can always find them again. It's using the same infrastructure as the memory caching to recognize files. So we'll look at all the input ports that are upstream, so all this part of the workflow, create a hash of that and use that hash as a file name and copy it to some location. And then down here I can do some data analysis, and when I change something about the data analysis, I don't have to rerun the entire thing. So here, for example, I had run it previously, so these pointers are blue, which means they weren't executed, because when it got to the persistent directory, it found the old results and used them again. So where do you find those files actually? On Linux and Mac, they're .vistrails/persistent files. On Windows, I actually don't know where they go.
Same location?
Same location, okay. You can change the location. So you could, for example, have it look in different locations. You could change a lot of things in the preferences of the persistence. Okay, now I wanted to say something about the ALPS modules. So there's kind of two more or less separate groups of modules. Some of them related to the ALPS library and the ALPS applications. So they really give you access to this is what we just saw in the last presentation. You can run ALPS applications, simulations, set up your parameters and all that. And then there are the dataset modules, which are more or less completely independent of the ALPS library or the ALPS application. And they basically try to implement a scriptable plotting and data analysis tool. So you have, of course, plotting, you have some fitting. Of course, you have a lot of numerical functions available in the SciPy library. So some of that stuff appears in the dataset module. Okay, so yeah, I explained the history already. One important thing to note is that the undo of VisTrails is implemented by the history. So if you undo something in the pipeline, it will just go up in the history. What that also means is that you don't have an undo in the history. So you could delete a branch in the history, but you cannot undo that. So that's going to be gone for good. So even though there's an undo button in the history, it doesn't store a history of the history. So that's dangerous. Okay. Then about the parameters, how we set up parameters for the ALPS applications. So this is something that will occur in all the tutorials. So I'm just dragging together two parameters here. So I have a fixed parameter j, which I set to 1, and then I have this iterate parameter in range. So I'm going to iterate a parameter j1 between 0 and 1 in 10 steps. This is just a random example. And then once you drag it together into this parameters module, what the parameters module will do is we'll take the outer product basically. So we'll basically, we have it's a list of dictionaries, the output. Each dictionary describing the parameters of one run. And so you're going to have one where j is 1 and j1 is 0.0 and so on. So if you put them together like this, it's always going to be the outer product. So for example, if I would take another iterate parameter in range that would iterate j2 in 10 steps, I would have 100 simulations. So you have to be careful with that. If you, for example, want j1 in 10 steps, and you will also want j2 in 10 steps, but you don't want the outer product, there's the merge parameters module that will do that. So you can avoid the outer product. But implicitly, it will always be done. Okay. Something about the dataset modules. So the dataset modules all work based on the same class, this dataset class. What does it contain? This is just basically if you look at the source, it's not much longer than this. So it contains the member x, y, and properties. So x and y are usually NumPy arrays, storing your data, and props is a dictionary that will contain all the information about this data. So all the parameters that were used in the simulation, once you perform a fit on the data, you could store the fit parameters into this dictionary. Whatever you feel you might need later on, just put it into this dictionary. And yeah, most modules, well, all dataset modules only work with this class basically to exchange data. So that's why they are kind of independent from the ALPS library in ALPS applications. Usually they actually operate on lists of these classes, so you can work with several data sets at the same time, of course. And it will imply the loop over all of them, so whatever. Like if you make a plot of a list of data sets, it will just create several lines. Yeah, and the plotting tools will also read the information from this props dictionary. So if you, for example, want to change the line width, you can set some number into the line width member of this dictionary, and the plotting modules will look into this, and there's all kinds of stuff. So for scatter plots, line plots, much of the commonly used functionality, label, for example, also. Error bars are also done. That happens automatically if you store into X and Y a data type that has a mean and an error. And we provide these data types in PyAlps and PyAlia. So I won't go into this too much at this point, but you'll notice that when you load the data of some ALPS Monte Carlo simulation, it will automatically create these data types. And they also support error propagation. So if you do some calculation, it will recalculate the error correctly. This is all in this module. Okay, now I'd like to put together a very simple workflow, just plotting this pretty simple function and putting a label on it. This is the most basic thing we could do. So I'm just going to start with a constant dataset module. It has two input ports, the length and the value. So let me make an array of length 10, and the value is 1. Now let's say I want to plot that. I need to take this prepare plot module, and now I have to connect the two. So I take the output port of this one, and as I said, it automatically connects to the right type of input port. So I don't have to look through all of these, just drag it down. Now let me show this. Again, drag it down. And this is probably the most simple work that you can do. Just make it constant function. Pretty boring. So let's make it a bit more involved. I'm going to take one of the transform modules. So these allow basically arbitrary transformation on these data sets. So if you click on the arrow, go to Edit Configuration, you get this window. And here you can just enter any Python source, any function that you want performed on this data. And you can make use of X, Y, and props. So for example here, I want to plot the function y equals x squared. So I'm just going to override the y member of all the data sets that come into this transform module and set them to x squared. Okay, let's execute it. And here's our y equals x squared plot. Yeah, let me make it a bit more fancy. I said that we can control all the plotting functions with the dictionary. So I'm going to set a label. So into the label member of this props dictionary, I put this string, and you can use any later here, as you can see. Now nothing happens. Why is that? I have to enable the legend. So I get a legend module and connect it to the prepare plot.
So if we cannot find those modules here in the search,
means that that our ALPS is somehow not connected to the VisTrails?
Yeah, but have you enabled? So have you, okay, that's one thing. Yeah. So once you've run the installer, you have to enable the ALPS module. So if you go to VisTrails preferences,
The simpler is you open one of the ALPS VisTrails files,
does it automatically?
and it automatically enables.
Okay. But if your installation went correctly, it should show up in this list and you can enable it, or maybe just open a file. And then they should show up on the list here. Okay, I've executed this, and here's my plot with the legend. Or using the label.
Should that be under VisTrails? That option is under VisTrails?
I don't, what, using Windows?
Yeah.
I have no idea what it is on the Windows. You're like, maybe edit preferences?
Preferences, yeah.
Okay. So, just say. So any questions about this workflow or how to put it together? Does it make sense? Okay. Okay, now I want to go into some slightly more advanced things. So there's something, so I said that most of these modules operate on a list of data sets. Which is kind of not very practical if you have a lot of different data sets. Say you run a simulation for different values of, okay, I have T and V here, so maybe some hopping and some repulsion term where you have Hamiltonian. You don't want such a flat list. What you can, and for example, if you want to extract the minimum over T or something like this, it will be very cumbersome because you will have to look for the right entries in the list, etc. So that's why we have hierarchical data sets. So you can make more structured lists. So you can have a list of lists of data sets, for example. And some modules will know how to deal with that automatically. And in some tutorials, for example, the exact diagonalization tutorials, you will see that it's quite useful sometimes for extracting some information. And then there's functions for creating these groups, flattening the groups, etc. The spreadsheet, yeah, so here you may have noticed that whenever I execute it, it puts it into a different cell of the spreadsheet. It just keeps moving down. If I want to fix it to something, I can take a cell location. And for example, fix that it goes into column 1. You know, probably doesn't like me because I've enabled it. Yeah. So using the cell location, you can just fix it. Okay. Exploration, I said I wanted to say well about the exploration. So for example, this workflow will perform some fit, and you want to make a fit over some range. For example, I don't know, extracting critical exponents, you may want to do that. And so I have this restrict X-range module here that will restrict the range on which I do the fit. And I want to try several values, and I don't want to rerun things all the time. So I can go to this exploration window, and then here I get a list of all the inputs of my workflow. I can drag it over here, and I can tell it to tune that parameter from, in this example, I did from 1 to 3. And then if I click execute, it's going to run the entire workflow for all values that I've chosen in the exploration. So I can kind of automatically scan some parameter range, and it's going to give me a whole list of plots. Okay. And yeah, there's one suggestion. So if you, the problem on Mac is that if you start the application from the icon, you don't get the error messages. So this is the command line to start it. If you want to see all the log messages and error messages. And then there's a screencast introduction to VisTrails, basically repeating how to put together the very simple workflow. Okay. Any questions? But that's what the screencast is there for.
Like in this,
Screencast basically repeats also that.
Is this online?
Yeah.
Earlier, I know you were saying that it's not.
I do have this.
Is this all? Was this so quick? Yeah.
Yeah.
I can't even get
Yeah. That's actually something we're working on right now, but not done.